I'm Tim. This PCB Sync.
Originally, I wanted to use a VNA to actually measure an antenna in this episode. Then I was going to read the impedance on the Smith chart. But here's the problem. A lot of people still don't have a VNA. Does that mean you can't learn about the Smith chart? Of course not. We can start by using online Smith chart tools. By entering a few typical impedances, you can first learn to see where each point is and what it represents. Then, when you actually get a VNA and see real measurement points, you won't be totally confused. It's like learning to read a GPS map before you actually drive on the highway. You can understand it just like you would a GPS map. Now, the first page of the Smith chart can look a little intimidating. There are a lot of circles and numbers, but for beginners, just remember four things. The center point is the 50 ohm point. The closer you are to the center, the better the match. The left side usually represents lower resistance, and the right side usually represents higher resistance. The upper half of the chart represents inductive, positive GX, while the lower half represents capacitive, negative GX. You don't need to memorize all the formulas right away. Just ask yourself three questions. Is this point far from the center? Is it on the left or the right? Is it on the top or the bottom? If you can answer these three questions, you've already understood most of it. That's more than half the battle. Now, let's continue looking at this Smith chart tool. Let's start by entering 50 ohms plus 0. Now we can see that this point is at the center, which is the most ideal spot. In a 50 ohm system, seeing this basically means everything is fine. Your VNA won't start lecturing you. Now, let's make some changes. First, let's directly change the resistance and set it to 25. IM is still 0, and now we see that this point has moved to the left. This indicates that the resistance is too low. Even though it doesn't have inductance or capacitance, it's no longer 50 ohms, so it will reflect. At this point, what the matching network needs to do is pull the point back to the center. Since the resistance is too low, we just add a resistor to bring it back. We're short by 25, so we add 25. There you go. Now it's back. So do you know what it means when the resistance is too low, too high, or whether it's more capacitive or more resistive? That's what we're talking about. It's about how to pull it back and giving everyone a general direction. Now, if we change our E to 100, we see that it moves to the right. This is what we just talked about, when the resistance is too high. Look, even though both are pure resistors, the positions for 25 ohms and 100 ohms are completely different. So the Smith chart isn't some kind of mystical thing. It's just a way to plot the position of the impedance. Now, let's change it again and set Re to 25. Let's also set IM to 25. Now we see that the point moves to the upper half of the circle. The upper half usually represents inductive characteristics, meaning that besides resistance, this load also has a bit of inductance. A lot of antennas or RF ports end up looking like this when measured. It might seem mysterious, but the point is already telling you where the problem is. So what should I do if I want to correct it? Since it's shifted toward inductive, I just need to add a capacitor. You'll see the point move downward. Now, let's decrease the value of this capacitor. Or if we increase the value of this capacitor, it'll keep changing. We can try a few different values. With 3 picofarads, it's already very close to this line. Then, with 2.6 picofarads, we can adjust it right onto this straight line, just like before, because of the resistor. If it's still off, we can add a 25 ohm resistor, and it will return to the origin. This way, we can debug it in a very targeted manner. Now let's try changing the imaginary part to negative 25. At this point, you should notice that it moves to the lower half of the circle, which represents capacitive reactance. This is exactly the opposite of what we saw earlier. So in the future, if you see the point above, think of inductive reactance first. If it's below, think of capacitive reactance. This is much easier than staring at a bunch of numbers. Now, let's go back to the image. Looking back at this diagram, you'll find the pattern is very simple, 50 ohms plus G0. When the point is at the center, the match is very good, and that's our ultimate goal. The point at 25 ohms plus J0 is on the left, which means the resistance is too low, so we need to increase the resistance. If the point is on the right at 100 ohms plus here, the resistance is too high, so we need to add a parallel resistor to lower the resistance. The point at 25 plus G25 is above, so it's inductive first. At 25 minus, this point is below, which means it's more capacitive. So the points on the Smith chart aren't just for decoration. They're telling you where your current load is, how far it is from 50 ohms, and which direction you should adjust next. A lot of engineers mess up debugging because they just start swapping capacitors without looking at the point or the direction. Congratulations, you've just activated the random adjustment package. Finally, remember this quick reference chart. The first point is this. The center represents 50 ohms. The closer you are to the center, the better the match. The upper half is inductive, the lower half is capacitive, the left side is low resistance, and the right side is high resistance. The farther you are from the center, the greater the reflection usually is. So before you debug any matching network, first read this point, then figure out how to bring it back to 50 ohms. The Smith chart isn't some alien map. It's for RF engineers. Thanks for watching.